Now, the next question, which is revision 5, still under integrals, is to find the surface integral. But on question 1, we are going to derive the differential surface element, which will help us solve our problems in surface integral. In short, we are going to find this value here, ds. And that is the first question, 5 marks. Finding ds. So let a surface S be defined explicitly by the function z fxy by parameterizing the surface with the position vector r xy as a function of x and y, and calculating the orthogonal tangent vectors. Derive the expression for the differential surface area element. So the first thing, let's parameterize our surface by x and y. So the first thing, we are going to parameterize S with x and y. So that is what we're going to do. Now, our position vector is defined by r as a function of x and y to be equals to xi plus yj plus zk. But remember, our z is a function of x and y. So it means we'll have xi plus yj plus f of x and y k, which is our z. So the first thing, let's parameterize our s with x and y only. Now the position vector, as we are told, is a function of x and y, meaning it will be xi plus yj plus zk. And z is given by, because our surface is defined explicitly by the function z, which is a function of x and y. So once we can get differential element ds, then we are good to go. Now, let's find the vector in the x direction and the vector in the y direction. So from our position vector, we can find a vector in x direction. We can call it r of x, which we get by differentiating x we are differentiating r with respect to x. So we'll have the r vector over dx will be equals to d partial derivative of d with respect to x r for xi plus d with respect to y for yj, then plus, here we are going to differentiate f with respect to x because we are looking for, no. Let me stop that. So this one is with x. We are differentiating with respect to x. So we are going to have dx here, then df over dx. And this is k. Good. So we are finding our vector in the x direction. And I need to do the same so that we don't repeat. So we are going to find the vector of our position vector in y direction at the same time, which will be ry. Now we find that by differentiating r with respect to y. Then this one will be partial derivative with respect to y for x I plus partial derivative with respect to y for y, j, and then plus partial derivative with respect to y for f, which is our z, and that is k, that. Now working simultaneously, we work on x and we work on y. Let me just create this space down to the end. We'll do the problem in the next page. Now what happened here? We can multiply this here. So what do we have? So dr, which is the same as our rx vector, will be, I will just multiply here by dx and also the whole thing by dx, so that I remove the dx here. Now when I do that, dx with respect to this will be 1i, so that will be I. Now plus 0j, because this is y, then plus df over dx, that is k. Now on the other side, we want our ry in the that means our position vector in the direction of y. So again we multiply by dy. So times dy, and again times dy. So dy and dy will go. So the whole thing here I forgot is now times dx. Now here we want now our position vector in y direction. So what are we going to have? The first case is 0i because we are differentiating x with respect to y. The second case is j because we are differentiating y with respect to y. And the third part is d over dy, but this is f. And the whole thing here, you multiply by dy. Now we are good. We have our vector in x direction, rx, and then we have our position vector in y direction, which is ry, which we have here. Okay, now we know that in geometry, we have already covered that in vector, that the area of the parallelogram are defined by the two vectors. Of course, I need to write that. We already did that before. I don't know if this is revision 1 or revision 2. We know that the area defined by the parallelogram and the area of a parallelogram, the area of a parallelogram, if you remember the cross product when we did that, parallelogram defined by Rx and Ry as the adjacent, if you remember, at the adjacent sides, is simply the magnitude of the cross product. So the area, if you remember, is simply the magnitude of Rx cross Ry. We did that from some examples, I don't know, in revision 1 or revision 2. The area of the parallelogram defined by the two vectors we have here, Rx and Ry, is simply the magnitude of the cross product of the two vectors. And to get the cross product, we simply need a determinant. Same thing we have been using. So we are applying it here. Now we have I, we have j, and we have k. Now our Rx, remember, our Rx is defined by the following. At I, we have 1. No, let me use blue. At I, we have 1. You can see 1. At j, we have 0. At k, we have df over dx. Now, on ry, we have 0, and then we have 1 at j, and then we have df over dx. Good. Now, we need to get our 3 matrices from this. What do? Remember, to get the 3 matrices from here, the same thing we do. We want I, we are going to close I, then j is negative, they remain that, because it is I cross k, which is clockwise. Then k is positive. I demonstrated that in the Cartesian coordinate system, which we have that. So our matrix will be formed by the following. If you close I, our matrix is 0, 1, then we have df over dx, then we have df over dy. Oh, sorry, this one was dy. I'm wondering that. Now, that one will be I. Good. So that will be our I. Then j is negative and k. Now for j, what do? For j, we close j. When we do that, our vector is 1, our matrix is 1, 0, 1, and 0. Okay, I think I made a mistake here. For I, let me just come back. I'm going to do that again. No, it was right. I think that was right. For I, we have 1, 0. Yeah, it was right. It was almost. So for j, we close this. Let's move on. For j, okay, we close j. If we do so, we have 1, 0, and then we have df over dx, and then we have df over dy. Now, the last case, we want k. For k, we close k. If we do that, we have 1, 0, 0, 1. Now our work is to get the determinant. Main diagonal minus the other. Main diagonal minus the other. Main diagonal minus the other. So we are getting the determinant, and then we get the magnitude. That will give us the area of the parallelogram formed by the 2 vectors as at the adjacent sides. So when we do that, then we have our black pen here. We'll get our I, then we'll get our k, our j, sorry, then plus we'll get our k. Now let's move. Now on I, we have 0 times df is 0 minus df dx times 1 is just df dx. But let me use blue to continue making it neat and lovely. So we have 0 minus df dx, which is times 1, is just df dx. That is I. Let's see j. On j, we have 1 times df dy will simply be df dy minus, that one is 0, because df dx times 0 is 0. On the other part, we have 1 times 1 is 1 minus 0. So our vector which we form is negative df dx I, then minus df dy j, then plus k. I hope this is okay. Hope that is clear. Now, the area is equals to the magnitude. So area is equals to magnitude of Rx cross Ry. I've defined that on top there, which is simply the square root of Rx is into bracket for the square root, our Rx cross Ry is this. So the square root of x squared, which is df over dx r squared, then plus y squared, which is negative df over dy squared plus 1 squared, which is our z squared. So it means our area will simply be square root, if we simplify, of 1. I can start with 1. 1 squared is 1 plus, no, I may be confused with that. So we start with our x, which is df over dx square plus our df over dy squared plus 1 squared, which is 1. Now our ds will be defined as area dx dy. How does that come? Come here. Remember our Rx had dx and dy. So when you find the cross product, I should have written here. Now our ds will be our differential element of area will simply be the cross product, which is Rx cross Ry. Then remember the Rx is dux and Ry is dy. So we bring them outside here and say dx dy. So our final answer is this. The ds, which is our differential small element of area, is square root of df. Remember our f is just the same as z over dx square. Remember our f was z into dz over dy squared plus 1 squared, if you like. And then outside we have dx dy. So this is how we derive that. So your question was calculate the orthogonal tangent. By calculating the orthogonal tangent which you have done, derive the expression for the differential surface area element. The equation is dz over dx squared. Remember our f is just z. Remember here. Our f was z here. The whole of this is z. So dz over dx squared plus dz over dy squared plus 1 squared, then dx dy. So that is how we work with that problem. So we have derived our differential surface area element. Now we need to apply it to this problem. Now, first, let's parameterize our curve as usual. The way we did line, let's parameterize our curve. The first thing, ds, we already know, is simply the square root. I've derived that on top of dz over dx squared plus dz over dy squared plus 1, and then dx dy. Good. That is our ds. We have derived there because we need to replace this ds. Now, let's get it. So from here, we'll have square root of our dz over dx. Remember, z is equals to 4. So if we differentiate z with respect, so d4 over dx, then u square plus d4 over dy squared plus 1, and then dx dy. Remember, this is 0 because you are differentiating a constant. This is 0. Also differentiating a constant is 0. Then square root of 1 is 1. So this simply becomes dx dy, because this is 1, which is simply dx dy. So we are moving well. Now that we have that, the next thing we need to set up our limits. So what are our limits? Let me write. So the limits is for x, it is running from 0 to 2. And for y, the limit is from 0 to 3. So that is what we have. Now, let's define our integral and then we work it out. So our integral is this s into x plus y ds. That is what we were given. Now we mean the first one, we are going to have our y because our ds is dx dy. So dy is outside. Please check, dx is inside, dy is outside. So our first integral is for dy, which run from 0 to 3. Then our inside integral is x, 0 to 2. Then we have our x plus y, then dx dy. Remember, y is the outside integral. The limits of y is 0 to 3. And then the inside integral is our dx, which is 0 to 2. Good. So the first thing, we are going to integrate with respect to the inner one first. We are going to work out this. And then we come to the outer one. So we are going to integrate with respect to x. So first, let's integrate with respect to x, the inside one, with respect to x. Then we'll finish with the outer one. So when you do that, remember when you integrate with respect to x, we have x there, so it will be x squared because you are adding 1, then you divide power law. Don't know whether to remind you, x power n, if you integrate, it will become x power n plus 1 over n plus 1, then plus c. So our n for x here, here x is power 1, and here there is x power 0 next to it. Written, not written, there is x power 0. Good. So we are going to have plus x power 0 become now x when you add 1 plus 1, then y. Think that is okay. Then we are substituting from 0 to 2. Remember, when we do, c will cancel, so we don't need to put c there. So when you substitute this, the thing we are going to get is, when you substitute the upper bound, you are going to have 2 squared over 2 plus you substitute 2y. If you substitute this, you remember plus c, because we have plus c here. Then do the same. So the whole thing here minus, when you substitute the lower bound, which is 0 squared over 2 plus 2 times, that is going to be 2 times 0 times y, which is just 0, then plus c. Now that is what I say, C cancels, so C will go. Now this one is just 0. When that happens, what we are going to have is 4r plus 2y. That is what we are going to have, 4 plus 2y. But this is 4 over 2, yes, so it will be 2 plus 2y. Now that is our first integral. Now we need to perform the outer integral. So we have, so let me write it again. Now we are going to integrate with respect to y. So we are going to have integral from 0 to 3, the outer one which was y, 0 to 3. Integrating now what we have is 2 plus 2y, sorry. That is what we have, 2 plus 2y, but now dy, because that is what we have. So when we integrate that, okay, so this will become, when you integrate this, it will be 2y, because there is y raised power 0 here. When you add 1 and you divide by 0 plus 1, it becomes 2y. Then let's proceed, plus 2y squared over 2, because we have power 1, 1 plus 1, 2 over 2. Now plus c, you're substituting 0 to 3 for y. Now when you proceed with this, you get 2y plus y squared plus c, that is 0 to 3. On the upper bound, you have 2 into 3 plus 3 squared plus c. On the lower bound, we have plus, the entire thing is 0, because when you substitute 0 is 0, then when you substitute y there is 0, then plus c. So again, c goes. So when that happens, our answer will now be 6 plus 3 squared is 9. And this gives you 15. This gives you 15. 6 plus 9, 15. So that is the answer for the surface integral x plus y, where S is a flat rectangular surface on the plane z is equals to 4, bounded by 0 to less than or equals to x, which is less than or equals to 2. Then 0 is less than or equals to y, which is less than or equals to 3. And this gives you 15.